Now we go on with the next topic of understanding the non-ideal voltage effects. In continuation, we have something called as leakage. So what is leakage? Conduction even when transistor is cut off. So even though the device is on, there is conduction going on, which is not desirable, and this is called as leakage. So this can happen because of substrate to diffusion junctions are reverse biased. Actually, the junctions which are present in the substrate should not conduct, but the process of conducting is called as leakage. We have something called as subthreshold region. Even before the device reaches the threshold voltage, the device starts conducting, and that is called the region before the threshold voltage is called as subthreshold, because threshold voltage is the minimum voltage required for the device to go into on condition. But even though it is less than the threshold voltage, sometimes there can be current flow, and this current can be called as subthreshold conduction. So the MOS device is partially conducting for gate voltages below threshold voltage. Sometimes it can conduct. So this is termed as subthreshold or weak inversion conduction. The process of conducting, making the device to go on in the subthreshold region is called as inversion conduction. We have something called as tunneling. So ideally, MOS device has high input impedance, as already told, and therefore there is no current flow through the terminal. That means your device is safe because it is offering the high resistance at the input side. But however, carriers tunnel through insulating barriers with finite probability. In spite of all these things, but still the carriers can sneak inside through the insulating barriers. That is, it can overcome the dielectric medium and it can go into the substrate or go into conduction. So tunneling current is as significant as leakage or subthreshold conduction. So it is as violent because of this sneaking in of the majority charge carriers, there is current flow, and this can happen in the subthreshold region, or this is also called as leakage. So we need to overcome the tunneling current. How is this possible? Use a better dielectric material which has high permittivity. Which has high permittivity means it restricts this charge carriers to sneak inside and conduct. Therefore, high dielectric constant makes high capacitance and reduces the need to reduce the oxide thickness, because we know the oxide thickness is very thin. So instead of using silicon oxide, silicon nitride is a good candidate for such materials. So even if gate oxide is thin, current flows from gate to source or drain by tunneling through gate oxide, and therefore current is proportional to area of the gate. So you can overcome tunneling by using a better insulating layer. Temperature effects. So temperature also has an effect on the device and in turn on the mobility. So how it will affect the mobility? That is, mobility is the speed or the velocity at which the electrons move. So carrier mobility decreases with temperature. So direct statement which says that the mobility reduces as you raise the temperature. Threshold voltage decreases linearly with increase in temperature. So threshold voltage also, if it is supposed to be 0.2 VDD in NMOS, even before that moment it will reduce, and it can be less than 0.2 VDD because of the rise in temperature. So it has an adverse effect if there is a rise in temperature. Junction leakage also increases with increasing temperature. Circuit performance is generally worst. So cooling also can make it better, but we need to have the cooling techniques. So two types of cooling techniques: convection and actual cooling, active cooling. So convection is naturally leave it. but it will take time. Or otherwise you keep or insert fans inside, which makes the cooling effect, or use heat sinks. So whatever heat is there, that is just reduced. Or in other way, it is active cooling externally. So externally you try to have a water cooling system or liquid nitrogen. So these has to be generated inside, and care should be taken to overcome this. But at the same time, cost also has to be justified. So implementing all these techniques can become a little cumbersome and expensive. Therefore, we have to see to it that the temperature effects are to be reduced, even though it is not nullified, to one extent, and try to vary with other parameter. We have something called as impact ionization, or it is also called as hot electron effects. So as the length of the gate decreases, electric field at drain increases. So as the length gate is reduced, short gate, the field is also increased. So for submicron length, because we are considering micrometers, E is so much that electrons are of high energy and is termed hot. So when the length is reduced from millimeters to micron, the field is so strong such that the electrons are of high energy, and they are termed here as hot. So these electrons attract holes towards drain from substrate and causes substrate current. So who are of high energy will attract the positive charge carriers which are present in the substrate and thus start conduction. This is called as impact ionization, and therefore the device is degraded. So this is another effect of non-ideal effects, or something which is not desirable. So try to avoid the leakage current flowing, because you already know about hot electron effects. Drain punch through. So when drain is at high voltage, the depletion region may extend to source, thus causing current to flow without gate voltage. So even though the gate voltage is not given, control is not there, the movement of the majority carriers are from source to drain, from source to drain, but which should not happen. Generally when the gate voltage is 0, everything should be 0, but it is not happening, still it starts conducting. This has to be overtaken, and this is called as drain punch through. We have next called as the noise margin. So what is noise margin? It is the allowable noise margin that has to be present in input without affecting the output. So no way the output has to be affected whenever you are having variations in the input side in terms of noise. So the noise margin have two different representations, NML and NMH, which is in turn defined as V input low maximum minus V output low maximum. Similarly, NMH is VOH minimum minus VIH maximum. So terminologies which is equivalently represented for NML and NMH. So we need to understand what is VIL, VOL, VOH, VIH. If you want to understand this, we have to consider the voltage transfer characteristics of inverter, which is shown in the next slide. So when you look into this, you have the transfer characteristics, and the bottommost on the, and transfer characteristics means this is your x-axis is your input, y-axis is your output. On your input you can identify VIL and VIH. Similarly on the output you can identify VOL and VOH. Now what are these VO high and low, or in turn VIL and VOH. You can also represent here, you can also show here logic 0 it is output, for logic 1 it is input. No, sorry. For logic 0 it is shown as VOL and VIL. From logic 1 it is VIH and VOH. Or in other words, there is a sharp curve. You can see in the inverter characteristics there is a sharp curve.